This example is dedicated to the thermal conduction Fourier's law. According to the Fourier's law, the heat flux in the flat wall is directed from the hot surface to the cold one and is calculated using this equation. Here, lambda is the thermal conductivity of the wall, d is the thickness of the wall, S is the area of the wall, and this is the temperature difference. Now for this particular wall made of plastic with thickness of 1 cm and the surface area of 10 by 10 cm square, the heat flux will be 16 watts. Let's simulate this case in QuickField. I start QuickField, create the new problem, Fourier's law. This will be the problem name, and this is the location of the files. Now here I choose the problem type. In fact, QuickField could simulate a steady state and transient heat transfer problem. In this case, we have the static thermal problem, so I choose the steady state transfer problem type. And the length units are centimeters. The wall Z dimension is 10 centimeters. Now here you can see the Geometry Model Editor window. I can close the window and open it again clicking the Edit Geometry Model button. Here I should draw the rectangle representing the vertical cross-section of the wall. The wall thickness is 1 centimeter. I should zoom in. The wall thickness is 1 centimeter and the wall height is 10 centimeters. So this is the rectangle. To draw the rectangle, I use the insert mode. Now I should assign labels to the geometrical objects. I switch to the select mode, select the block, open the properties dialog and type in the label wall. You see the label automatically appears here in the tree. Now the left side is cold, and the right side is hot. Next, I should assign physical properties to the labels. For the cold side, I double-click the label name, and here I type in the temperature, plus 20 degrees Celsius. For the hot size, again I double-click the label name and specify the temperature plus 60 degrees Celsius. And for the wall, I specify the thermal conductivity is 0.4 watts per Kelvin meters. Now I can build the finite element mesh. Just press this button and run the simulation. Here you can see the temperature distribution in the wall. Now let's verify that the heat flux is directed from the hot side to the cold side. I open the Field Picture Properties dialog and switch on the vectors of the heat flux. Let's zoom in. You see, indeed, the heat flux is directed from the hot side to the cold side. To measure the heat flux value, I should build the integration contour. I can build the integration contour in different ways, and the only requirement is that the contour should cross all the heat flux paths. So I can build it like here. I can build it along the hot surface. Let's build it along the cold surface. I will switch off the color map so you can see better how the contour looks like. I click this edge. You see it becomes green, and this is the contour. Now I go to the integral calculator and I calculate the heat flux. You see it's 16 watts, and here is the direction of the flux. And I can also calculate the surface area of the wall. See, it's 100 centimeters square, like it was specified here. You can find the simulation files following this link at our website. Here is the page. You can see the description of the example, and here is the download link.